Hey, I'm Evan Barras, a PhD student at the University of Mexico, and today I'm going to talk about a quantum algorithm to simulate Lindblad master equations. This is joint work between me and my PI, Milad Marvian, and before we get into the details, let's refresh a bit about open quantum systems. An open quantum system is a quantum system that is embedded inside some unknown bath that can interact and perturb the quantum system. And in general, one of the more popular models for open quantum systems is a model where we assume that this bath is large relative to the size of the system as well as memoryless. And such a model has been successfully used to describe diverse phenomena ranging from spontaneous emission in atoms as well as ZZ crosstalk in superconducting transmon qubits. And given such an open quantum system model, this model is described by what is called the Lindblad master equation, which relates the time derivative of the state of the system to a superoperator acting on the system called the Lindbladian. And the Lindbladian in general can be decomposed into two different parts. The first part of which is just our good old familiar von Neumann equation for a closed quantum system. While this second part involving the L terms is typically called the dissipator, and it's supposed to model the interactions between the system and the unknown environment, and also has all of sort of the classical randomness baked into it. And in general, these L operators are typically called jump operators, and I'm using M here to denote the total number of jump operators for this dissipator. So given the task of simulating a Lindbladian, we can choose two different approaches. If we choose a classical algorithms-based approach, then we're immediately hit with the problem that current classical algorithms are inefficient. And on top of that, complexity evidence suggests that efficient algorithms are unlikely to exist. And this is due to the fact that simulating Lindbladians is complete for the complexity class BQP. And even if we restrict to the case of only dissipative dynamics, so we only have like a dissipator, then this problem still ends up being BQP complete. So even purely dissipative dynamics is thought to be hard to simulate. On the other hand, if we choose a quantum algorithms-based approach, then all of the current algorithms are actually efficient. And on top of that, we have a multitude of various approaches to choose from. We have product formula-based approaches, linear combination of unitary-based approaches, as well as a recent truncated Duhamel expansion-based approach. So the motivation behind this project was when we were originally looking at these various different approaches used to simulate Lindbladians, the one thing that was kind of common between all of the various different approaches was that they don't really seem to exploit a lot of the natural physics involved within the Lindbladian, and more specifically, they don't exactly exploit the fact that this dissipator term in the Lindbladian has classical randomness naturally baked into it, because we're modeling an open quantum system where this environment has some classical stochasticity baked into it. And so for an example, a lot of the common approaches treated simulating Lindbladians as just simply solving a differential equation, not leveraging the fact that there is this classical randomness involved. And on top of that, a lot of the current approaches also treat both the Hamiltonian dynamics as well as the dissipative dynamics on equal footing. And the price we pay for such an approach is that the resource costs for such algorithms explicitly scale with respect to the number of jump operators in the dissipator. And this can be sometimes problematic, and a case where this happens is the case of global depolarizing dissipation. We know this dissipator is quite simple to simulate. You can exactly solve the master equation, and it simply amounts to flipping a couple coins and choosing the right n-qubit Pauli operator to implement. But it turns out that this dissipator has an exponential amount of jump operators. And so if you just naively try to plug it into some of these general purpose algorithms, you get a blow up in your resource costs. So our goal with this project was just to better design, just to design quantum algorithms to better leverage the physics and specifically the classical randomness baked into the Lindblad master equation, and to find specific cases where we can actually exploit this fact and save on some resources. So at a high level, our approach, we take an approach where we basically just split up this Lindbladian superoperator into its von Neumann equation component and its dissipative component. And then for a small time delta t, we create two different subroutines. One subroutine to approximate the closed system dynamics, and another subroutine to approximate the dissipative dynamics for a small time delta t. And this dissipative dynamics portion has the classical randomness baked into it. And so in order to implement this, we implement the dissipative simulation subroutine using a simple sampling procedure that we perform in the compilation of our quantum circuits. One caveat of our algorithm is we've restricted the algorithm to simulate Lindbladians, where the dissipator itself generates a quantum channel for a small time delta t that's approximately a probabilistic mixture of unitary operations as well as fixed state preparation. And ideally, these unitaries are efficiently implementable. Even though our model is restrictive, there are dissipators that fit our requirements, such as both global and local depolarization, as well as dissipation, where these jump operators generate a CP map that prepares a fixed state. So our algorithm in general iterates R times these boxes, which are composed of two Hamiltonian simulation subroutines and one dissipative simulation subroutine. And then for each of these dissipative simulation subroutines, we apply our sampling protocol in the compilation phase of the circuit. And our sampling protocol just simply amounts to the fact that we're going to sample over these various unitary operations and fixed state preparation operations that, when averaged out, approximate our dissipative evolution for a small period of time. To summarize, the result of our project is that to simulate Lindbladian for up to time t and up to epsilon, precision epsilon in diamond distance, our main algorithm requires R many calls to these unitary operations and fixed state preparation operations that, when averaged, approximate our dissipative dynamics, as well as any Hamiltonian simulation subroutine you choose. So we leave it open to the user to pick the Hamiltonian simulation subroutine that works best for their problem. And an additional added benefit is that there are no ancilla qubits that are needed beyond what is required to implement the Hamiltonian simulation subroutine. So essentially, if you choose a Hamiltonian simulation subroutine that requires a small amount of ancilla qubits, then your entire algorithm will only require that many ancilla qubits. In addition to the main result previously described, we also generalized our algorithm to 3 separate cases. We extended the algorithm to include time-dependent dissipation. We also generalized our dissipation model through the use of ancillary qubits and provided an extension of the algorithm to include some types of non-Markovian dissipation. In order to show point number 1, we proved a time-dependent second-order product formula for Lindbladians to extend the analysis. And in order to prove point number 2, we also showed how to have the ancilla cost for a dilation through dilating as a probabilistic mixture of unitaries as opposed to a single unitary. And so in essence, when you do a Stein spring dilation, half of those ancilla qubits are just used to model the classical randomness of the system itself. And to wrap things up, some open questions we've been thinking about have been how to generalize this dissipation model to go beyond this simple model of mixing unitaries with fixed state preparation. A more general open question would be how to extend these quantum signal processing type algorithms to simulate open quantum systems. And finally, one final open question would be how to analyze the costs for our time-correlated dissipation extension. And thank you for your time. Here is the QR code as well as the archive number for our paper.